In the last lecture, I was talking about 3 dimension. X-axis, Y-axis, Z-axis. Let us take a point P whose coordinates are X, Y, Z. Origin O, from O to say L, this much is X. OL is X. Then OM is Y. And let us draw a perpendicular, that is N. This much is X, mm, and lm is Y. Okay, and pn is Z. So from origin to L is X, then L to N is Y, then L to P is Z. We will reach at the point Z in this way. And these are the Cartesian coordinates. Now, if we take as r, theta, z as the cylindrical coordinates, then ON is r, which makes angle theta with x-axis, and Pn is Z. So from this triangle OLN, this much is 90, angle OLN. So from here, as we have done in the last lecture, that the relation between Cartesian and polar coordinates, same here, x equals to r cos theta, y equals to r sin theta, and z equals to z. So these are the relations between Cartesian coordinate system to cylindrical coordinate system. Cylindrical coordinate system is one of the orthogonal curvilinear coordinate system. Now I will discuss spherical polar coordinate system, which is another orthogonal curvilinear coordinate system. X, Y, Z, origin O. Let us take a point P whose Cartesian coordinates are x, y, z, and spherical polar coordinates are theta, phi. Okay? So in a similar way, we will take now OP is R, which makes angle theta with z axis, and let us join ON xy plane. So this is 90 degree. So from the triangle OPN, we have ON by OP equals to, this angle is theta. Why? Because these two are alternate angles and they are same. So ON by OP, that is perpendicular by hypotenuse, is sin theta. So ON is R sin theta. So ON is R sin theta. Now from the triangle OLN, here angle OLN is 90 degree. So OL by ON is, this is base and this is hypotenuse, base by hypotenuse, that is cos phi. So x equals to R sin theta cos phi, and ln by ON, ln by ON is perpendicular by hypotenuse is sin phi, ln is y. So y by R sin theta is sin phi. So y equals to R sin theta sin phi. Now from this triangle OPN, here we can find PN by OP equal, PN is base and OP is hypotenuse. So this is cos theta. So PN, that is Z, equals to R cos theta. Therefore we have x equals to R sin theta cos phi, this one, and y equals to, here is a, y equals to R sin theta sin phi, and z equals to R cos theta, z equals to R cos theta. So these are the relations between Cartesian coordinate system to spherical polar coordinate system. Now this system can be used to solve some problem of motion. In the last lecture, I have shown you that if the position of a particle on the surface of the earth position of the particle on the surface of the earth, and if the earth revolves around the sun, then the motion of that particle is towards a central force. And to find the motion of that particle, we can use this spherical polar coordinate system. The solution of that problem will be easier. Here I am not talking about non-Euclidean space. Obviously, cylindrical coordinate system and spherical polar coordinate system, both of them are on Euclidean space. Both of them are applicable on Euclidean space. About non-Euclidean, if we think about that, if a light ray coming from a far away galaxy gazing towards the sun, then the light ray will be deviated from its rectilinear path, and the deviation is 1.75 second, and that is due to the curved space-time. So there we will use the Riemannian geometry. In another lecture, we will discuss about Riemannian geometry, which is obviously non-Euclidean, not also pseudo-Euclidean, that is Riemannian.